So we will start today with Craig, and met Craig many years ago when he was. I'm just like 4 years older now. And I remember that Igor asked me if I could be on the PhD defense committee at the time. And I was very nervous, the first time in my life in a PhD defense committee. But it went great, and since then I know Craig and people. So, Craig, thank you for coming, thank you for being here to talk about homology of Hurwitz spaces.
Thank you, and thank you to all of the organizers for what has been a really lovely conference so far, and I hope not to change that in the next hour. Yeah, let's see. So I think maybe in some sense this talk is fitting in spirit with the conference. There will be some algebraic geometry involved, although it's not really the algebraic geometry that I think is the focus of the conference. And there will be some group actions, but they will not be the sort of groups that we've been focusing on. But hopefully there'll be a bit for everyone to enjoy. It will be all over the place between algebraic geometry, algebraic topology, category theory, and the theory of Hopf algebras. So if you find you're in the middle of the subject that you don't feel very comfortable with, don't worry, it's going to change. There we go. All right, so let me begin with talking about the objects that I want to study. This is a rather forbidding definition unless you're an algebraic geometer. Don't worry, I'm going to talk about the complex points in just a moment. So our background setup, G is going to be a finite group. And then I'm going to pick a subset of G, which is closed under conjugation. I'm going to call it C, and a positive integer. And then there's a moduli scheme which parameterizes branch covers of the affine of the projected line called the Hurwitz moduli space. So it has what does it do? It parameterizes maps from a curve to P1, and that curve is going to be a branch covering. So there's a divisor, which is the branch locus of the covering, and away from that divisor, this is actually a cover, it's a G-Galois cover. So the number n is telling me the number of branch points. The degree of the divisor in the affine line is n. The map is ramified on the branch locus on the divisor where it's ramified. But the purpose of the subset C is we are going to force ourselves to only consider branch coverings where the monodromy around these branch points lies in the subset C. And then last and hardest to motivate is we're going to ask for, so this is a branch covering of P1. There's a point at infinity and an infinitesimal tangent vector pointing out from there. And I want to trivialize so that we're going to ask for the fiber to be trivialized over that tangential point. So it's not ramified at infinity. It's not ramified on an infinitesimal neighborhood of infinity. It can be ramified at infinity itself. Yeah. Nowhere in here did I insist that sigma needs to be a connected curve, which is common to insist. So I'm going to write C for the subscheme which parameterizes the connected. I'm going to jump into the topology on these spaces and the complex points of these things. But before I do, can I answer any questions about what this object is? What is the angle in yes, well, so if I take a K point of this scheme, it is it defines the function field of the curve that comes from it, defines a a G-Galois extension of the base field KT, and that it's also regular. So it's the closure of K, of this K inside of here is just K. And so this is a solution to the regular inverse Galois problem. If you find a K rational point that on this variety, then you solve the regular inverse Galois problem. If your field is, say, a number field, then Hilbert's reducibility theorem tells us that in particular also gives a solution to the inverse Galois problem for that field. So that's one reason to care to the rational points of this scheme parameterize solutions to the regular inverse Galois problem. That's terrifying. That's a hard problem. And I'm not going to be focusing on that at all. My interest in this is to study the points of this variety over a finite field, where the number field, function field analogy, global field analogy lets us address questions about number fields, lets us translate questions about number fields into questions about function fields, where we can try to solve them here. These are similarly Galois extensions. It's just now that they're Galois extensions of a function field. And so there are various conjectures of Gunther-Mahler and Cohen and Lenstra about the distribution of these extensions. And so if we can control the size of the set of FQ points of these schemes, then we can address some of these function field conjectures. So that's my motivation. And now let me rapidly switch into topology. So let me talk about the complex points of the scheme. I want to study the scheme. The way that I want to study it is by studying the cohomology of its complex points. And I can tell you exactly what the topology of the complex points is. So the configuration space of points in the plane is a space of subsets of exactly n elements. So we can write it down as n tuples in C, where they're distinct n tuples in C. And then we modify the action of the symmetric group, which reorders them.
Those x's are these, right?
Sorry.
Okay, that's not.
Yeah. It was x's before, and I changed them to z's because they were complex numbers, and then I apparently didn't change them all. Yeah, sorry. Yeah, the x's are z's. So this is probably a favorite object for many people in this room. So I'm probably not telling you things that you don't already know. But this space is a K-1 for the braid group. Braid group is has this beautiful presentation. The sigma I is can't use the board. It's generated by sigma 1 through sigma n, and sigma I is this braid, the one that swaps the I and I plus first strands. And so and the braids commute if they're far enough apart, which is maybe apparent from that picture. And if they're right next to each other, they satisfy something that's unsurprisingly called the braid relation. Sigma I plus 1, sigma I is sigma I plus 1, sigma I, sigma I plus 1. So this space, the covering space, is the base of a covering map from the Hurwitz space. So this is map to the configuration space. What does it do? It takes the data of this branch covering of the affine line, and it forgets everything about it except the branch locus. And since we assumed that the degree of the divisor of the branch locus is n, there are n points and n branch points, so we get n points in the configuration space. So that's the base of the fibration of the covering space. The fiber is the following. So how do I reconstruct the branch covering from the branch locus? I have to tell you what the covering map is. And I can classify covering maps, actual covering spaces, by homomorphisms out of the fundamental group to my deck group, G. So the fibers are on from the fundamental group of G, but the fundamental group of C minus n points is a free group on n generators. So that's just G cross itself. But remember that remember that we insisted that the monodromy around the branch points lies in C, this fixed subspace. So rather than having all of G to the n in our fiber, we just have C. That's the fiber, and I can completely describe the topology of this space if I tell you the actions of the fundamental group of the fiber. And the effect of the fundamental group with this braid group on the fiber is something that Hurwitz discovered. So the ith generator permutes an n tuple as follows. It leaves most of the n tuple alone, but it swaps the ith and I plus first. But along the way, it conjugates the I by the n plus first. So my notation G to the H means right conjugation by G by H. Great. So that's a complete description of this space. And that description gives us an immediate way of computing the homology of these Hurwitz spaces. Because the base of my fibration is a k pi 1, the homology of the base is the homology of the group, braid group. But now, because it's a covering space, I can rewrite the homology of the total space of the covering space as the homology of the braid group with coefficients in the local system, which is the permutation representation given by the fiber.
So you linearize that.
I linearized it. Yeah, I've taken this notation means take that set and take the k vector spaces.
Consider it as a local system.
Yeah, I mean, consider it as a representation of the braid group. Yeah. So again, why do I care about the homology of these spaces? If I'm interested in these questions of Mala and von Lenstra and so forth, if I want to count points on the Hurwitz space, I can do so by using the Rotnik-Lefschetz trace formula that asks me to compute the cohomology of the Hurwitz spaces as well, the Hall cohomology of compactly supported Hall cohomology, but for the purposes of this talk, you're welcome to consider that as being the same as the singular cohomology. It is isomorphic. But because this is an algebraic variety, that in this case is defined over FQ bar, it carries an action of the absolute Galois group of FQ bar, and one can compute the number of points as the alternating sum of traces of the action of the generator of the Galois group for Venus.
What the L is?
L is not Q. L is a prime other than Q, other than P, which is the so Q is the power of P.
Yeah.
So I'm looking at the cohomology with L-adic coefficients. Again, because QL is flat over the rationals, I can actually do this computation over just Q and base change up to QL, and then get the domain that the Frobenius is acting on.
So you have whatever space over the algebraic logic.
Yes, so this is the Eiffel cohomology over FQ bar, and then there is a comparison of the FQ bar points to the Q bar points that then lets me then identify with the cohomology of the C. All right, so our goal is to compute this group cohomology. Spoiler, we're not going to succeed.
So sorry, Craig, so the action is the natural one given by the strands. They're reading the components.
This is the action.
Oh, that's the action. Oh, okay.
So they permute them, but they braid them, but they conjugate them.
say a bit about how the trivialization that the invisible neighborhood of infinity goes into?
Sure. So when we classify covering spaces, they're not classified by homomorphisms out of fundamental groups, but by conjugacy classes of homomorphisms.
Right, yeah, this is
This rectifies that. Yeah. So if I don't include that trivialization, this is an orbifold, rather than a seam. So, I mean, you can work with that, and that's fine. But it's a little bit nicer.
Yeah. Thanks.
Sure. All right. So what I want to do is talk about how to compute this. And I want to get to it in a very roundabout way. And it's through the theory of braided Hopf algebras. So let me talk a little bit about those. And the setting is that of braided monoidal categories. So let me just remind you about the monoidal categories. If I have category C, it's monoidal if it's equipped with a bifunctor, we're calling it a tensor product, and an object one, which is the unit for the tensor product. And we want these operations to be associative and unital up to various natural isomorphisms, and I am not going to spend any time about the various axioms for coherences and so forth there. It's additionally braided if there's an isomorphism from the tensor product in one order to the tensor product in the other order. But we don't insist that the braiding squares to the identity, as is common in most of our favorite examples. But when it does, when sigma squares to the identity, rather than being a braided monoidal category, it's a symmetric monoidal category. So all of your favorite categories are symmetric monoidal categories, category sets with the cross products, topological spaces, also with the cross product, vector spaces with the tensor product over K. For instance, in this setting, the braiding, it just swaps the two sides. If I remove the circle, the same formula is true for set and top. But one of my favorite categories that's genuinely braided is the category of Dieter-Drinfeld modules. So if I specify my group G, then it's the same group. YDGG is the category of right Dieter-Drinfeld modules. So they're right KG modules, and they have a grading. They decompose as a direct sum that index over the group, and the action and the grading interact in the following formula in the following way. The action on a part in degree G by an element H lies in that part that's in degree G conjugated by H. So that's the interaction between the right action and the decomposition. The tensor product is what it usually is. The tensor product of graded things is the tensor product of, and then you give it a grading by summing over degrees that multiply to be your big degree that you're starting in. But the braiding is non-trivial. Rather than just swapping A and B, I swap A and B, but along the way, use the action of the group. So if W is in the H component, and when I move it past B, W stays the same, but B gets acted upon by H. So you can quickly see if I do this twice, I'm not going to get back to B times W unless the group is trivial.
I suppose these are the same things as representations of the double G.
Yeah. So a very concrete example is the vector space, which is the group ring on G. Its right action is by conjugation, right conjugation, and the decomposition is the sort of eponymous grading. Something the element G is in degree G. So this is probably very familiar, but one of the reasons that this is called a braided monoidal category is because one of the axioms that I suppressed, there's an equality of the maps from A tensor B tensor C to C tensor B tensor A, which says if you braid in this order, that the first two, then the last two, then the first two, it's the same thing as braiding the last two, the first to the last two. And if I draw the picture of what this is doing, do the first, do the second, do the last two, do the first, and then do it in the other order, then if I think of these as braids, they're equal because they're both equal to the full twist, or half twist rather, in the braid group. And so because that was one non-trivial relation in the braid group, this means that if you have any object in C, I get an action of the nth braid group on n-fold tensors in the where the where that braid acts by the braiding on the I to I plus first term. Just some advanced warning. I'll call V finitely braided if this action factors through a finite collision. So this is a familiar action. Actually, the Hurwitz action is this tautological action. So again, if I go back to here, I said the group ring is a Ytter-Drenfeld module. If KC is then a direct summand of KG, and it becomes the Ytter-Drenfeld module as well. And so what was the action? I move one past the other and conjugate. And so the action of sigma I, it says on the I and I plus first strand, I and I plus first elements of the n-fold tensor product, I move the I past the I plus first and conjugate. Well, that was exactly the Hurwitz action. So we have a rephrasing then that the thing we want to compute, the homology of the Hurwitz spaces, is the same thing as the homology of the braid group with coefficients in the n-fold tensor power of this particular Ytter-Drenfeld module, with tautological action coming from the structure of the category. So I've transformed the question in algebraic geometry in some sense to a question about group homology arising from the category. Which probably makes half of the audience very happy and half of the audience very unhappy. All right. One thing I want to say is that the structure of a braided category is precisely what you need in order for algebras, so monoid objects in your category, the tensor product of two algebras to be an algebra again. So if A and B are algebras, the multiplication on A tensor B is going to be as follows. I use the braiding to swap A and B, and then I multiply termwise, and that gives me a multiplication on the. All right, I'll leave that. That's a moment. So a braided algebra, so this is not a special type of Hopf algebra, but rather a Hopf algebra object in a braided nodal category. I want to write down the axioms. You know the axioms of Hopf algebra. Got a product, got a co-product, got a unit, got a co-unit. The product and co-product interact in a certain way, and there's the antipode. And if you don't want to worry about the antipode, I'm only really ever going to use the bi-algebra structure here.
So do you need them to have this property of having an antipode?
So everything I'm going to be working with are going to be connected. So the existence of a
Braided connected.
So it will be equipped with an automatically. We just remind you that the primitives in the Hopf algebra are the elements where the diagonal is the second simplest thing you can ask for, rather than being the group-like element in the Welstalk. The diagonal of A tensor one. The diagonal of A is A tensor one plus one tensor A. So one of the things that I swapped over was that one of the axioms for being a Hopf algebra is that the diagonal is an algebra map. The diagonal goes from A to A tensor A. But the thing is that A tensor A is made into an algebra using this product. In particular, it uses the braiding on my category to move A past A. So classically, that's, the diagonal, the multiplication is like A tensor B, tensor A prime tensor B prime is AA prime tensor BB prime. But now something rather complicated is happening. And it turns out that if my category is braided and not symmetric, this just introduces an infinite amount of complications that destroys all of the structure that we know. So there are, however, a bunch of classical examples. The tensor algebra on an object in C, so the free associative algebra generated by that guy. So the sum over all n of d tensor n. That's an algebra by definition. It's a coalgebra. It becomes a coalgebra when you declare V to be primitive. So that's a great example of a braided Hopf algebra. Its dual is a coalgebra, also sometimes called the quantum shuffle algebra, because
Sorry, what does it mean to be primitive? That V equals its span of the primitives?
so V is contained in the primitives, but it is not equal to the primitives.
Okay.
Yeah, so the primitives are in the tensor algebra. The primitives in the tensor algebra are quite large. In the classic setting, when V is actually a symmetric, V is in the symmetric category, the primitives in the tensor algebra are the free Lie algebra on V. Right. Yeah, so the tensor coalgebra is sometimes called the quantum shuffle algebra, and this is because by just declaring V to be primitive in the tensor algebra, the consequence of this is that when you write out the formula for the diagonal, which is implied by declaring V to be primitive, you just shuffle things past each other. And so when you dualize it, that turns into the multiplication on the tensor coalgebra. And then there's an object which is probably unfamiliar to most people in this room, which is called the Nichols algebra, and it's the image of the tensor algebra in something called algebra. So there's a unique Hopf map from TV to T co V, which is the identity on V. Right, this is the free algebra. This is the co-free co-algebra. So the natural map from the one to the other, and the image is called the Nichols algebra, or equivalently to the subalgebra of the tensor coalgebra generated by V. And this plays an important role in the classification of Hopf algebras. That I'm completely not going to do a good job of addressing, but for instance, the theorem of Mark Rosso, which tells you that if you're working in the category of Jäder-Drinfeld modules for Z to the n, and if you have a Cartan matrix, the n by n Cartan matrix, then you can build the positive part of the quantized and developing algebra as the Nichols algebra for a suitable object. So I hinted at the fact that there's a structure theory for Hopf algebras, which falls apart very badly for braided Hopf algebras. And so that's sort of where I want to go. Let me just see if anyone has any questions first. So the classical structure theory is as follows. So if A is a Hopf algebra, its primitives become a Lie algebra under the operation that probably was your first exposure to Lie algebras. The bracket of A and B is going to be A times B minus B times A. And so from a Hopf algebra, I can extract a Lie algebra from the primitives. And I can go back in the other direction. From a Lie algebra, I can construct a Hopf algebra from the universal enveloping algebra. So I take the free associative algebra, the tensor algebra on L, and I modify the relation that the bracket is equal to the fractal. And it turns out that this becomes a Hopf algebra by extending multiplicatively formulas on L, so the diagonal of an element of it. So like I make L primitive, so the diagonal of A is A to the 1 plus 1 plus A. I make the antipode of A the negative of A, and I make the co-unit of A 0. I extend all of those multiplicatively, and that gives me definition of a Hopf structure on the enveloping algebra. So for instance, like we were saying earlier, the enveloping algebra of the free Lie algebra on V is the tensor algebra. Read backwards, the tensor algebra, the primitives of the tensor algebra, the free Lie algebra. On the other hand, if we make L abelian, if we make all of the brackets 0, then what am I doing? I'm taking A times B minus B times A and setting that equal to 0. Therefore I've made this not the free associative algebra, but the free commutative algebra. So the theorem of Milner and Moore is that if I'm working in characteristic 0, these two operations are inverse to each other. So if A is for primitively generated Hopf algebras, there's a natural map from the enveloping algebra of the primitives of A to A, and this is a nice Hopf algebras. They, of course, also, I think probably more interestingly for many people in this room, proved a torsion, a mod P version of this, and the stuff that the braided story is already insanely complicated over the rationals, and we'll worry about torsion some other time. There's also the Poincaré-Birkhoff-Witt theorem, which says that if I take the enveloping algebra, I can filter it by powers of L, and then the associated gradient is the symmetric algebra, which is maybe not surprising. If you take the associated gradient of this relation, the bracket drops out, being of lower filtration than the A times B minus B times A. Right. Okay, so I want to do the same thing for braided Hopf algebras, and I have a problem. So if A is a braided Hopf algebra, the primitives of A are not a Lie algebra any longer. So let me write down the proof for why the primitives in a normal Hopf algebra are a Lie algebra, and see what goes wrong. So normally the diagonal, so how do we do it? We need to show that the diagonal of the bracket is bracket times 1 plus 1 plus the bracket. So I compute the diagonal of the bracket. It's a Hopf algebra, so the diagonal of A times B is the diagonal of A times the diagonal of B, and then minus the diagonal of B is the diagonal of A. A and B are primitives, so I expand these things out. Boom, boom. And then multiplication, then I do multiplication. All right, so if I multiply the A tensor 1 times the B tensor 1, I get this A B tensor 1. And similarly with the A tensor 1 times the 1 tensor B, I get A tensor B. But now when I multiply the 1 tensor A times the B tensor 1, I have to use the braiding category and move this A past this B. I don't have to worry about that with the 1 tensor A times the 1 tensor B, so then I just get 1 tensor A times B. And then the same thing in the other order. Now, if my braiding is just swap the two factors, then this is B tensor A, and this orange guy cancels this orange guy. And the green guy cancels the green guy. But if the braiding isn't of that form, they don't cancel. So this stops being. So if they cancel, right, then I get AB tensor 1 minus AB minus BA tensor 1 tensor AB minus BA, and I see that it's primitive, but these obstruct the primitivity. That's a problem. You can say, what is it? What structure does it have? I mean, I can't take the enveloping algebra that's not even a Lie algebra. So you can play around with it for a little bit and find sort of a stand-in for the bracket. If I'm working in a finitely braided situation, so if the order of the braiding is finite, and let me set the order of minus sigma to be n. Then I can define a new sort of bracket. There's going to be 1 over n times the alternating sum of twist I many times and multiply. And if you want to stay out for the next couple of minutes, convince yourselves that this is that if you modify this argument, you can get that this guy is primitive. There's a Jacobi relation in normal Lie algebras. Is there a Jacobi relation here? I don't know. I think it's going to be insanely complicated to write down. Yeah, which there is. So we're starting to see there's some structure to the primitives, but we don't really know what it is, and there's it's sort of stressful because I don't know what to ask of it. And then we remember that we're algebraic topologists, and we're good at describing the structure of algebraic objects in a category. The right thing to do is talk about operads. So let me do that. So let me talk about braided operads, following a definition of Hurwitz. So a braided operad is some sort of gadget which encodes algebraic structures, because they're braided operads, they're algebraic structures in braided modular categories, which are defined by n to 1 area operations. So our tautological example is the endomorphism operad of an object in my braided monoidal category, and it's an nth. The nth term of this guy is the set of maps in my category from the n equals tensor power to a to itself. And what does it come with? There's an action of the braid group on a tensor to the n, so there's a resulting action of en on the nth term of the operad. And there are various structure maps which allow me to compose maps within maps. So F circle I of G applied to this complicated set of inputs says apply G in the ith spot to these m terms, and then that gives me one term, and I regard it as something in the ith spot, and I apply F to, I put that in the ith spot and I apply F to. That was probably the least coherent description of the endomorphism operator I've ever given. And then there are various associativity and equivariance axioms about the order of compositions and how the braid group act and interact with the inputs and so forth. And if I write them down, they'll be here for the rest of the day, so I won't do that. And then a braided operator in general is going to abstract these properties away in the same way that a group abstracts away the representation. Right, so if O is an operad and A is an object in my category, it's an O algebra if it comes with a map from O to the endomorphism operad. And equivalently, that's simply saying that O parameterizes, ON parameterizes an area operations on A with various actions. So,
Correct.
yeah.
What was Spirowicz's original motivation for incorporating the braiding?
So he constructed he proved a recognition principle for the E2 operad. And the insight is that if you, because the E2 operad, because its spaces are k-pi1s for the braid groups, their universal covers are contractible. And proving a recognition principle for contractible things is easier than proving a recognition principle for things with complicated homotopy types. But if you have a setting in which your structure group is now the braid group, then rather than the symmetric groups, you can trade the k-pi1 for the braid group with the contractible object. We'll see in some sense his construction in supplement. So some very concrete examples, the braided associative operad. Sure, I love this notation, but is given by the group ring on the braid groups, and its algebras are associative algebras in a braided model category. So why is that? If I act, so what do I need to do? Elements of the nth braid group are supposed to now parameterize n-area operations on an algebra. So I apply the braiding, I use the braid group to move them around, and I just multiply. So just as in the associative operad, it's the symmetric group that allows me to commute the terms and multiply. Now the permutations are coming from the braid group. The braided commutative operad is similar, except that I forced the action of the braid group to be trivial, taking the co-invariance. And its algebras are braided commutative associative algebras, so guys for which the multiplication in one order is equal to the multiplication in the other order. What does that mean? If I do the braiding and multiply, it's the same thing as just multiplying. If I have an operad, the free algebra on an object is constructed in this fashion. I tensor v with itself n times, and then tensor it over dn with on. So for instance, the free algebra over the braided associative operad is the tensor algebra, because what do? I take the group ring on Bn, I tensor it over Bn with v tensor to dn. Two wrongs make a right, and these just go away. That leads to the end. That's my tensor algebra. And then similarly, the free braided commutative algebra is gotten by taking the tensor algebra and taking the braid co-invariance in the nth terms. There's a topological example. We'll get back to Manuel's question. So the little discs operad is a symmetric operad in the way we normally think about it in the category of topological spaces. But I can think of a symmetric operad as a braided operad. This is a map from the symmetric group, the braid group to the symmetric group. And I can only just draw the picture that we all draw, or I'm telling you about the composition. If I want to plug this picture into this picture using the two-area of the circle 2 operation, I shrink this circle down, put it in the second spot, and get that, and then erase the boundary lines, and then renumber things accordingly. Right. So why is this relevant in our talk? The terms of the little discs operad are the configuration space. If I mod out by the symmetric group, so the ordered configuration spaces if I don't. And because homology is a monoidal functor, Lax monoidal functor, the homology of an operad is an operad. So the homology of E2 becomes an operad, and one interpretation of part of Fred Cohen's thesis is that the top part of the homology, E2 of n, is a sub-operad of that homology, and it's isomorphic to the fifth of the lead operad. So I say this because our problem in Hopf algebra situation is that we don't know what a Lie algebra is supposed to be. And here is a topological description of what the Lie opera is supposed to be. So what I want to do is I want to look at the following construction. I'll apologize for the pro part of this. Let's form an inverse system. Let's study the inverse system of all finite sheeted regular covers of the terms in the little disc alpha. All equivalently, all finite sheeted regular covers of the configuration space. This is an inverse system by just covering spaces form an inverse. And I can lift, so Hurwitz's construction says it is the same thing, but rather than taking finite sheeted regular covers, he just takes the universal cover. And he says, if I pick base points appropriately on the universal cover, then I can lift the structure maps at E2 to the structure maps on the universal cover. And we're going to do the same thing. We're going to take, we're just going to do it in this inverse system of finite 2D covers. And that gives me a operad structure, braided operad structure on this tower of covers of E2. And I'll call that E2, call that operad E2 then. But it's not an operad of spaces any longer. It's an operad in the inverse system, in the category of inverse system. That's unfortunate. But one of the nice things is that the free objects are what we want to compute. So the homology, if I compute the homology of E2 thin, and if B is finitely braided, and if I'm working in characteristic 0, then I can identify the free object on the homology of E2 thin with the homology of B and with coefficients in the homological representation of B, considering it's all finite. So this then, if we go back and say our where were we? Our goal was to compute the homology of Hurwitz spaces. We reinterpreted that as the homology of the braid group with coefficients in the tautological representation, the tautological action on this Yetter-Drinfeld module. Then this tells me the thing that I want to compute can be rephrased as a free algebra over this operand, homology of the finite 2D covers of E2. So we can rephrase our question then as, let us try to compute the structure of this operand, the new form of the question. I don't know how to do that. I can tell you some of its homology. So the bottom homology, the 0th homology, it's connected. Taking finite 2D covers of connected spaces, still connected. So this is a trivial representation of the braid group. At 0th homology is the braided commutative operand. Just as in the classical case, the 0th homology of E2 and the commutative operand. Let's define the braided primitive operand to be the top dimensional homology of this tower. So again, it's a tower of spaces. So this becomes an operand in row vector spaces. So I can finally tell you a theorem. So that if we're working in characteristic 0, and if A is a finitely braided Hopf algebra, then its primitives form an algebra over this. And let me argue that this construction isn't done by saying that the free algebra over this operad is equal to the primitives in the tensor algebra. Exactly, this is the braided analog of this statement that the where is it? The primitives, well, it's gone now. The primitives in the tensor algebra are the freely algebra on B. Oh, I think I have it right here. Yes, the primitives in the tensor algebra are the freely algebra on B. So this is at least capturing free objects. So to me, it's just that it is the correct notion for Lie algebra, replacement notion of a Lie algebra, or if we want to encapsulate the primitives in the data. The Lie operad is generated by binary operation, by a binary operation, the bracket. And all of the higher operations are composite with these things. And that is really false for this thing. So something that we proved is that there are non-trivial indecomposable operations in every area. There's a 3-area operation, which is not a composition of 2-area operations. A 4-area operation is not a composite of 2 or 3-area operations, so on and so on. It's a very complicated object, but at least at the bottom, it's generated by this thing that we described. That's sort of a norm version of the bracket. So I feel like we understand the bottom of the homology of this thing. and then we understand the top homology of this thing. If you look at parentheses, something I'm not saying here is also that the whole homology of E2 is the Gerstenhaber operad, which can be written as the composite of the commutative and the Lie operads. So you might guess that the homology, all of the homology of E2 fin is the composite of the braided commutative with the braided primitive operads. This is false. There's definitely classes that are not there in that. I mean, there's a map from that operad into this operad, and it is. I don't know if it's injected, but it is definitely not surjected. So it's complicated.
Great.
Yeah.
Have sort of a tangent question. Is there some sort of statement that says like the Hopf homology of a braided associative algebra has the structure of a E-fin 2 algebra?
So
Or maybe this doesn't make any sense.
So, and the thing is that an algebra in a braided model category, you don't, when you're just talking about the algebra structure, you never use the braiding. So you can rely on the pre-existing clean conjectures for that.
Wait, so what's a braided associative algebra?
It's an algebra. It's an algebra object in a braided category. But the definition is still like you multiply and they're associative. It's just that there's more symmetries that allow you to permute things around. But there are, but it is a good questioning that there's sort of a different version of, which is a variant on the sort of Deligne type conjecture, which, for instance, you can look at the homology of you can look at the crowbar complex of a Hopf algebra, and similar. I mean, I think basically Adams knew this, but similar constructions, as in the proof of the Deligne conjecture, prove that that's an E2 algebra. If you're
taking the double loop space.
Yeah. I believe that it's still true. So, but now if you move that Hopf algebra and make it into a braided Hopf algebra, I believe that the crowbar complex is an algebra. I mean, if you assume that it's finitely braided.
That would be an example.
Yeah.
Is it somewhere?
Well, I can tell you the argument, but no, it's not. It's not written down anywhere. All right. Okay, let me basically try to finish up. So we've interpreted the homology. We've interpreted the homology of Hurwitz spaces in terms of the homology of this E2 fin. That's sort of the free algebra over this operad. And we've identified the algebraic structure that top and bottom homologies describe. I'd like to return to some of the algebraic geometry. And basically what I'm going to say is like it's awful. Right. So the little disks operad, I sort of want to start in the middle of the slide. The nth term of the little disks operad, right? These were the configuration spaces points in the plane. And that's an algebraic variety. So if I look over C, they're literally equal. But if I take the profinite completion of the complex points, that's the same thing as the equivalent to the all topological type of the configuration space over Q bar. And that carries an action of the absolute Galois group. Now, there isn't, as far as I know, an algebra structure on the actual configuration spaces in category of varieties So we don't immediately get a Galois structure on E2 hat. But Geoffroy Aurel interpreted some Drinfeld's construction of the Grothendieck-Tegeler group to show that the group of homotopy automorphisms of the profinite completion of this operad is the Grothendieck-Tegeler group. So the GT hat is a particular very difficult to describe subgroup of the automorphism groups, the profinite completion of the free group on two generators. And Belli's theorem tells me that it contains a copy of the absolute Galois group of the subgroup, and its conjectures that they're equal. But from Geoffroy's theorem, you can very quickly just lift this action. What is it saying? GT hat, or the Galois group, acts on E2 hat through operad maps, and you can lift that action up this tower on which she recovers, and get an action of GT hat on the terms of the homology of E2 then. It's no longer an operad action, and the reason is that the Galois group acts on the braid group. So it acts on part of the data of what it means to be an operad. So if you incorporate that, then everything sort of works out. So and at the moment, calling this a skew operad map, and maybe it's not a great name.
Sorry, can you remind me what E2 hat means?
It means the profinite completion of the terms in E2.
What does that mean?
So their homotopy type, for instance, are the K-pi1s for the profinite grid groups. But,
Oh, I see it.
yeah. So the depressing news is that the absolute Galois group, or the Grothendieck-Tegeler group, although it acts on this in a structured way, the action is faithful. Even on the simplest non-trivial part of the homology, the third term of the top homology of E2 then. And that's because you can prove that that group contains a copy of the group term on F2 hat, and if GT acts faithfully on F2 hat, then it acts faithfully on this. So that should be a warning that, like, when we're studying this operad, not to try to be too concrete as to what it is we're computing, because the answer is going to contain a faithful Galois representation. So that's going to be very large and complicated. I'll stop there. What I'm not telling you is that there is a sort of analog of the classical structure theory for braided Hopf algebras, but it's a rather complicated story to describe, and of course it doesn't fit perfectly into this talk. You want it to be built around the Milnor-Moore theorem to hold by saying, oh, there's the primitives of a Hopf algebra. Okay, we said these are algebras over this braided primitive operad. You can build an enveloping algebra. That's true. You can cook up a map, and it's surjective, but it's not always injective. And this is something rather unique to setting of braided Hopf algebras. So you can prove that there is a version of the Milnor-Moore theorem and also a version of the Poincaré-Virchow theorem in this setting, but it involves a much larger operad than the braided primitive operad. I'm happy to talk to you individually about that, but I don't know if that's something that you want to see me on the slide. Thank you very much.